Welcome to the Introduction to Calculus. I'm Mr. Stark. In this video, we'll kick off topic 3, which is titled More on Limits. There are 3 lessons. The first one is all about the limit definition. It includes some properties as well. You could follow along using this document, which is linked in the description. Let's get started. I have a review question for you, and there's no need to write this down. Find the points of discontinuity of the function. Number 1, f of x equals 5x minus 3 divided by x minus 3. We could graph this on a graphing calculator and find out if there's a vertical asymptote or a hole, but we could also use algebra. And the algebra says that if the denominator is equal to 0, there's a vertical asymptote, unless the numerator is a multiple of the denominator. And in this case, 5x minus 3 looks like it could be, but it's not a multiple of x minus 3. So therefore, there's a vertical asymptote at x equals 3. We find that by setting x minus 3 equal to 0 and solving for x. Now, in number 2, g of x equals 5x minus 15 divided by x minus 3. Notice that 5x minus 15 is a multiple of x minus 3. We get that by factoring out a 5. So 5 times x minus 3. Because x minus 3 divides out with x minus 3, then that means that there's a hole instead of a vertical asymptote at that same point. So we find that by setting that binomial equal to 0 again. So we get x minus 3 is equal to 0, so x equals 3. It's really helpful to use algebra to find points of discontinuity because we'll also use algebra to evaluate limits. I have one more thing to share with you before the actual lesson, and it's this: a graph of the integer function and a question. What is the limit as x approaches 2 of the integer function? Do you know? Whether or not you know, it's a good question. Because look at the graph. When x equals 2, the function's value is 2. That's where my cursor is at. But if x is in between 1 and 2, then the function's value is 1. So what's the limit's value? Is it 2? Is it 1? Is it something else? I'm going to leave that question hanging until the next video. Now it's time for the actual lesson. Let's talk about the limit definition. Jot this down. The limit as x approaches a of f of x equals L. That expression, what that means is f of x gets arbitrarily close to L as x gets arbitrarily close to a. And what that means practically is, let's suppose you take a point and you plot it on a function. As the x value approaches a, so as we move that point left or right on the coordinate plane, then that means the y value or the f of x value is arbitrarily or approaching closer and closer to the y value, L. Let's do an example. Find the limit as x approaches 2 of x cubed minus 8 divided by x minus 2. Recall from the review that when the denominator is equal to 0, we might have a vertical asymptote or a hole. And in this case, when we plug in 2 to x minus 2, we get 0. So it definitely could be a vertical asymptote. But I'm a little hesitant to go with that because it looks like the numerator is a multiple of the denominator, meaning x to x cubed and 2 to 2 cubed, which is 8. So here's the approach. We'll always use algebra first, if possible, then a table, then the graph. So let's evaluate this limit in that order. So first, algebraic. This expression is equal to the limit as x approaches 2 of x minus 2 times x squared plus 2x plus 4. That's what x cubed minus 8 factors down into. And the way that you could do that is a mnemonic called SOAP. So it's same sign, opposite sign, always positive, S-O-A-P. So that you can notice the same sign in x minus 2 as x cubed minus 8. And then opposite x squared plus 2x, that's opposite of the minus in the original numerator, and then always positive plus 4. And then you could test the numbers and the terms. So that's all divided by x minus 2. Notice we could divide out the x minus 2's, those two binomials divide out. And when we do that, that's the location of the whole when you solve x minus 2 equals 0. So the location is x equals 2, which we kind of knew already. So that's all equal to x approaches 2, the limit as x approaches 2 of x squared plus 2x plus 4. And now that we don't have a denominator, we could plug in anything we want, any real number, and we'll get a real answer. So when we do that, we get 2 squared plus 2 times 2 plus 4, which is equal to 12. So what we originally thought was an issue, like there's a vertical asymptote or a hole, like we can't get a function value, it's undefined, that the limit actually has a value. So the function's undefined, but the limit is defined. Now let's approach this limit on the calculator. So let's turn your calculator on and go to y equals and enter this function, and you could pause the video. Then let's go to your table set, so second window, and make sure you have 0 and 1. So 0 for the table start and 1 for delta table. And then press second graph, which is the table. And you should start at 0, like the topmost x value should be 0. And you see that you could go down to 2 by pressing the down arrow. And then if you arrow right, you see that there's an error at x equals 2. So just because it says error doesn't mean the limit doesn't exist. What that means is the function is undefined at that point. Okay, now let's go to the graph. So if you press zoom 6, you won't get the full window of this function, so we'll change it a little. Notice that if you do, so second trace and just plug in a value, if you plug in 2, it won't be on your screen. So what I want you to do is change your window. So press the window button and just make your y max go up to 15. That should do it. By doing that, we'll be able to see the y value when you plug in 2. So once it's finished graphing, what you could do is press second trace, which is the calc feature, and then press enter on value, and then you can plug in 2. So what I want you to see is that when x equals 2, y is nothing, not 0, but undefined. It doesn't give you a value. It's not defined. But if you press trace now, you can see that you're really close to x equals 2, like x equals 1.97 perhaps, and that the y value is 11.8. But if you arrow right to a little bit bigger than 2, like x equals 2.1, you'll see that the y value is above 12. So that's a little hint that when the y values are above and below a specific value, that the limit is that value, which is 12. It's not always super clear, but it helps. There is a more formal definition of the limit, but now is just not the time. Instead, I'd like to share some properties with you. There are 7 of them. They depend on this statement. If the limit as x approaches c of f of x and the limit as x approaches c of g of x both exist, then the sum rule is the limit as x approaches c of the sum of two functions, such as f and g, equals the limit as x approaches c of f of x plus the limit as x approaches c of g of x. Meaning if you take the limit of a sum, it's equal to the limit of the functions added together. Just so you know, I'm going to write the limit as x approaches c 14 more times. So you could either come up with a shorthand way to write that, or just practice writing limit. The next one is the difference rule. The limit as x approaches c of f of x minus g of x, so functions being subtracted, is equal to what we'd kind of expect, the limit as x approaches c of f of x minus the limit as x approaches c of g of x. The third one is the product rule. The limit as x approaches c of the product of two functions. Yep, you guessed it, is equal to the limit as x approaches c of f of x times the limit as x approaches c of g of x. The fourth one is the quotient rule. The limit as x approaches c of the quotient of two functions, such as f of x and g of x, is equal to the limit as x approaches c of f of x divided by the limit as x approaches c of g of x. But in this case, the denominator cannot be equal to 0, meaning the limit as x approaches c of g of x can't be 0. Number 5, the constant multiple rule. The limit as x approaches c of some constant k multiplied by f of x is equal to, we could factor out that k times the limit as x approaches c of f of x. Number 6, the power rule. This one, we're raising a function to a power. The limit as x approaches c of f of x raised to the n power is equal to the limit as x approaches c of f of x, all raised to the n power. Finally, number 7, the root rule, which we'll do an example with next. The limit as x approaches c of a function in which we're taking the nth root of, so the nth root of f of x, is equal to the nth root of everything, the limit included, the limit as x approaches c of f of x. And that's valid for n is greater than or equal to 2. So we have to be taking at least the square root or the cubed root or the fourth root and so on, numbers greater than 2. I'd like to point out how the properties are similar to those of real numbers. In other words, they're fairly consistent with what we'd expect them to be. Our last example is a unique one. Find the limit as x approaches 0 of the fourth root of sine x over x. Remember our approach to limits. First, algebraic, then tabular, finally graphical. So let's take the algebraic approach first, which really just involves using the properties. Notice that we can apply the root rule, so our limit is now equal to the fourth root of the limit as x approaches 0 of sine x over x. Everything is inside the root. Now it looks like we could use the quotient rule because we have sine x divided by x. So those are like the two functions that are being divided by each other. So we have the limit as x approaches 0 of sine x divided by the limit as x approaches 0 of x. Oh no, the denominator is equal to 0. That means we cannot use the quotient rule. So we're back to square one here, and we really don't know what the limit as x approaches 0 of sine x over x is. In this case, we can't do any more algebra, so we must rely on a tabular approach or a graphical approach. Let's look at the table on a TI-84 graphing calculator. So if you have a calculator, you could follow along, turn it on, and make sure you're in radian mode. If you have a CE, you could see that you're in radian mode or degree mode. If you don't have the color edition, you just click mode. Make sure radian is highlighted. If not, press enter on it and then go to your y equals screen. First, we have to enter the equation in, then we could go to the table. Press alpha y equals and then enter to use the fraction notation. If you don't have that, then just divide normally. And then enter sine. It gives you an open parentheses. So sine is above the comma and the 7. And then enter x, close parentheses. And then arrow right to get to the denominator and just type x. You know, x is to the right of alpha. And then don't hit graph. Let's go to your table. Second graph. You should see your table now. And if your x values start at 0, that's great. If not, just arrow up or down until you get to x equals 0. And I like to place the 0 in the middle of my screen, so I'll go up a little bit so that 0 is in the middle. And then if I go down to x equals 0, I see that there's an error for that function, for y1. But that doesn't mean the limit does not exist. Let's get closer. So let's press second window and change your table start. So enter 0, and then for the delta table, enter 0.1. Then press second graph. Now your x value should change only by 0.1. Arrow up a few times so you could see what's to the left and to the right, aka above and below x. Now let's go to like negative 0.1. You should see that the y value is 0.9983, very close to y equals 1. And then arrow down, you could see that at x equals 0.1, it's a positive 0.9983. So we could get closer and closer and closer by doing 0.01 and 0.0001, and we'll end up noticing that the limit as x approaches 0 of sine x over x is 1. With that known, we could do all sorts of things with limits. So it's really helpful to keep that in your short-term memory. Now we could go to the graph. I mean, that was super helpful. So we know that the limit is 1. What the graph is going to show us will be consistent with that. So let's press graph. And if you have a normal window, that's great. You could also press zoom 7 for a trig version. It just makes the window smaller. And then if you press trace after your graph is being sketched, and you should see at x equals 0, the y value is undefined, but you move to the right or to the left, you could see that the y values are very close to 1. To finish this example off, the very next thing that we could do is we write the fourth root of 1, because the limit as x approaches 0 of sine x over x is 1, based on our tabular and graphical analysis. So we have the fourth root of 1, which is equal to 1. That is the end of lesson 3A. In the next video, we'll talk about one-sided and two-sided limits. Hey, I just want to thank you so much for learning with me. I appreciate you watching. Be sure to let me know if you have any comments or questions. See you next time.